Okay, so hi everybody. Nice to see you again. Okay, so we are now studying about basic detection algorithm. So-called, Viola-Johns algorithm. Okay. So last class, we have studied, how to calculate the features, right? So the highlight features, especially based on the, integral image. Okay. On top of the features, we also studied, how to calculate the error in every, iteration. Okay. So do you remember how to calculate the error? Okay. Yeah. So can you see this slide? Page 19, the weak classifier, titled weak classifier. Okay. So now I'm page 19. Okay. So this diagram is explaining the whole overall flow of AWS, learning very briefly. Okay, so let me review a little bit about, because it's been a week, right? So I want to review a little bit about the process, how to calculate the error. Okay, very briefly, very quickly. Okay. So, in the beginning, what do we have? In the beginning of the training, okay, AWS training, what is ready? What should be ready for the training? What do we have? Do we need to have in advance? Hello. Okay. So, Adam, you're a little late. Okay. So for AWS training, okay, what do you need to have in advance? Just before the training, what do we have to prepare? Okay, yes, space images. So more technically, you can say training dataset or training samples, especially when you say face images, it is positive samples. Okay. Yeah. So actually, you said, calculate the error for every feature. The error calculation, and feature calculation is actually the part of the algorithm, the AWS train. Okay. So before that step, so we have to prepare samples, right? That are the training samples, so positive samples and negative samples already. Okay. So we have to prepare that. So it is thousands of images, right? And then what do we need more? So to calculate feature, what do we need? We have to prepare 180,000. What? Remember the number? Yeah. Okay. So we have to prepare. Yes, exactly. Feature set, right? Features. It is in this case. Yeah, exactly. So in this case, we need 180,000 features. So we use the symbol F. And J is the index of the feature, okay? I is the index of the sample images, okay? Is it clear? Okay. And by the way, every sample image has weight, W. So W also use the same index I. Okay, so W is normalized, so sum of all the W equals 0, equals 1. Okay, so we have to prepare these two steps, the sample steps and feature set of features and set of samples. Okay, so on top of that, so the AWS algorithm is a kind of iterative algorithm. Okay, so every iteration we are calculating the error of every feature. So here the error is calculated per feature. Okay, and to calculate the error, as we answered already, we are using this formula. Let me draw the line here. Okay. So this formula. Okay. So remember the meaning of this formula. What is H here in this formula? What is H? Remember what was H in this formula? Error formula. System gas. System gas. Yes. Yes. Okay. Which algorithm? Yeah. More exactly, weak classifier. That is in the title of this page. Okay. Weak classifier H. H is representing, hypothesis. Okay. Yeah. So as I said, H is weak classifier combination of threshold and feature. So HJ. So J is per features. Every feature can have one weak classifier. So H is also using index J. So HJXI means you input X sample. X is the symbol for sample image, right? X sample into weak classifier J. So it means we are calculating feature J for Xi. Then it is, so this weak classifier is a binary classifier, right? So it is returning 0 or 1. So when the classifier say 1, it means what? Phase, exactly, yes. 1, phase. 0, non-phase. So what is Y? Y is label, yes. Label of every sample, okay? So when the label say 1 and H say 1, it means, oh, label, the original sample was phase. Y means the origin, what was the, label? What was it? It was phase or non-phase, right? When Y equal 1. By the way, the reclassifier say 1. Then the result of the reclassifier equals is true, correct, right? And when this term, the right term here, the absolute term, is becoming 0. By the way, whatever case, when they are different. So, for example, we classify say 1. By the way, original label was non-phase 0. Then this part is becoming 1. So this way, when the reclassifier fails, incorrect, then this part is becoming 1. Then W is accumulated to this error using this, sigma symbol. Okay? For certain symbol, for example, oh, the classifier was correct. Yes, was correct. Then this W is multiplied by 0, then 0 is added. So it means, the weight is not added. So when we have very good reclassifier, just assume, it's impossible, but let's say the reclassifier is 100% correct. Then what is error? Becoming 0. Is that correct? Because every weight is multiplied by 0. So error equals 0. In the worst case, when the reclassifier is 0% correct, so totally, incorrect. For every sample it fails. Then what is the error? Ej equals 1. It's becoming 1, right? Because, W was normalized. Okay, so the maximum value the error can have per every reclassifier is 1. The minimum value equals 0. So we are getting some value in between. Okay, so in this way, we apply this formula to every feature. Okay, so when we calculate the error of every reclassifier, we are applying this one to all the samples using this sigma. Okay, so we are calculating the error for reclassifier H1. We are calculating error for reclassifier H2. So in this way, we are calculating all the error until the end one, error 180,000. Okay. So once we have all these errors, then among these errors, we try to select just one of them. Here, the one means lowest error, ET. Okay, error ET, and that is becoming the best reclassifier at this moment, HT. So the corresponding reclassifier. Okay, so when we say lowest error, it means it has the minimum error. So that is the best. So 0, if there is any reclassifier H that has error equals 0, then that is the best one, right? But in reality, there is nothing that has error 0. So instead of 0, we are selecting the minimum one. Yes, exactly. Okay. So HT is selected among 180,000 reclassifiers. Okay, in this way, with the minimum error. It can be 0.1, 0.2, whatever. Okay, is that clear? Yeah. Okay, so that's what we have studied last week. Okay. Then here, what is T? HT, ET. What is this symbol? What does that mean? No. So that is a little bit confusing, right? Not the best, not the index of the best classifier, best feature. Okay. So here the T means iteration number, time. Okay, T. Okay. So HT means is one of them. Okay. But this T doesn't represent the index J, any of J. It doesn't represent J. Okay. So among 180,000 reclassifiers, okay, we select one, and that is stored into H1 in the first iteration. Okay. So from here, T means another separate index of the iteration time. Okay, if you are in the first iteration, then T equals 1. If you are now in the second iteration, T equals 2. So HT means the selected reclassifier in every iteration. H1, H2, H3, H4 until the maximum iteration. So this maximum iteration number is just defined by the engineer, okay, by people. Yeah, number of loops. How many loops, right? So what can be the maximum loop? Like 180,000, right? But we don't do that. We don't need so many features. So we are just setting the maximum number of loop based on the number of features, a number of reclassifier we want to generate. Okay? Yeah. So HT is selected every time. H1, H2, H3. Okay. So once HT and ET is selected from this tab, then based on the selected HT and especially its ET, error T, okay, we update every weight of the samples W in this way using this formula. Okay, W T plus 1I equals WTI multiply E over 1 minus E. Oh, what does that mean? E over 1 minus E. Anybody can say what it means? So you know what is ET, right? ET is current minimum error of HT, right? So based on ET, this ET can be any number between 0 and 1. It can be 0 0.4, 0 0.54, 0 0.234, okay, whatever, okay? So it can be a kind of some number in between 0 and 1, okay? By the way, we are multiplying E over 1 minus E to the weight. Giving less weight to the not good classifier. Yeah, yes, it's very close. Yeah, okay. So let's today we'll start with this weight. Okay, how to update the weight. Okay, let's discuss more about it. Okay. Okay. Anyways, this is the main process in every loop, and we discussed, how to apply, Okay, so in this page, in page 22, I'm just, briefly, going through the important slides. So reclassifier is mathematically defined in this way, HJX, okay? Reclassifier is taking input, sample image. Image is input. Then FJX, the feature is calculated and the feature is less than or larger than, theta, okay, the threshold, then it is phase, else it is zero, non-phase. Okay, here PJ is determining the direction of this inequality sign. Okay, sometimes the feature value should be less than some threshold, sometimes to be phase, right? Sometimes it should be larger than threshold to be phase. Okay, so it is different for every reclassifier. Okay, so we can determine this, threshold, and we can determine, this PJ, direction plus 1 minus 1 by analyzing, the feature values of positive and negative samples. Is that clear? Okay, so let me skip some detailed slides. So, so this is kind of formulation for every, feature, okay? So each one, so here, again, H1 means, this is index J, okay? Every feature, every feature F1, okay? First feature F1, we calculate the threshold and error, and then finally we can have the reclassifier H1. Okay. As for alpha, it is actually related to the strong classifier. We'll discuss about it later. Okay. Yeah. Let me skip. Okay, we have already discussed about this error calculation. Okay. So to update the weight, now we are multiplying this term E over 1 minus E. So it looks a little bit strange, right? So we know what is E. Is the error value between 0 and 1. By the way, what is this? E over 1 minus E. So this is actually kind of, transformation of the value. Okay, so let me show you. Okay, so this graph. Okay, So let's go to page 31. I'm trying to move the page to page 31. Okay. In page 31, as you can see here, this is the graph between E and beta. So here beta, so in the paper, this formula E over 1 minus E, that is represented as beta. Okay, E over 1 minus E. So this is graph in page 31 is showing the relationship between E and beta. Here the beta is representing simply, to simplify, E over 1 minus E. So what is the relationship between them? Can you see any special relationship? Okay, it looks like a kind of log-like, function. So what happens? Exponential. Okay. So when E is getting bigger, so when E equals 0, right? When there is no error, okay? Then what is beta? Beta is also 0, okay? When E is increasing from 0 to 1, what happens to beta? Beta is increasing or decreasing? Increasing, okay, yeah? So when the error is big, then beta is also big, okay? So in that case, in that sense, we can say their relationship is, first of all, proportional, exponentially proportional, right? Not just linear kind of proportional, right? Okay. So E is bigger, then beta is bigger. Okay. So as you said, okay. So as someone mentioned, beta is going to infinite when E is approaching to 1. So it means when E has very large error, approaching 1. So there is nothing in reality, there is nothing, no error, with the value of 0, value of 1. Okay, they can be 0.9, 0.95, blah blah blah. So it may not be infinite in reality, but it still can have very large value, much larger than 1. Is that correct? Because this beta function is kind of exponential. Is that clear? Yes. So in that sense, we can say beta is kind of amplification. It is amplifying the error. Okay. So E is just between 0 and 1, but beta can be much bigger number. Okay. Okay. So now we found out that E beta is exponentially proportional to E error, and beta is amplifying error to a large number. Is that correct? Okay, so is there any other special relationship between error and beta in terms of value? Okay, there is one more important relationship we have to know about E and beta. Anybody can see anything special? Yeah, exactly. Yeah. Minus, there is no minus range. Okay, so this is just graph, but it cannot be negative. Okay, yes. When E equals 0.5, I think SIS pointed out very important fact, right? So when E equals 0.5, then beta equals 1. Okay, because, so let me go back to the previous slide. Okay. So actually we are now discussing about, in this slide, page 30, we are discussing about step D. Okay, so this is now inside the iteration T. Okay, so in the step D, based on the error, we are calculating the weight W T plus I 1 plus comma I. Okay, T plus based on T WTI. So beta actually will be multiplied to W. So when we are yeah, yes. So when we are multiplying some value, then if the value is less than 1, it means the W is becoming smaller or larger. When E equals 0, yes, error equals 0, then beta is 1, the W weight is not changed, right? Yes, exactly. So when E equals exactly 0.5, then beta is becoming 1. So W is not changing. So this is kind of very short point. Okay. By the way, when E equals less than 0.5, it means beta is becoming less than 1.0, less than 1. Then W value is multiplied by a number less than 1. Then W is getting smaller. Okay. In other case, when error is larger than 0.5, then beta is larger than 1. Then W is getting bigger. Is it clear? Okay. So let me go to the next page again. Okay. So in this graph, in page 31, okay. So this 0.5 of error is kind of threshold according to this formula. Okay. So when error is less than 0.5, then we are decreasing the weight, every weight. Every weight? No, not every weight. I'm sorry. Anyways, we are decreasing weight. When error is larger than 0.5, we are increasing the weight. Okay, so this is very important, fact from this graph. Is that clear? Okay, let me go back to the previous slide again. Okay, so actually this is the formula. Okay, W is multiplied by beta. By the way, beta has one exponent component here. It is 1 minus absolute of h minus y. What's the meaning? Anybody can understand this formula? 1 minus h absolute of hx minus y. What is it doing? It's complicated, but actually it is very simple. But as a formula, it looks a little bit complicated. What does that mean? So we are here again. The I index is about sample, right? So here xi is representing the same sample of wi. Okay, the corresponding sample. Yes. Okay. So let's say okay, when h minus 1 minus y, hx minus y equals 0, when they are the same, it means 1 and 1 or 1, 0 and 0. It means the successful classification. So this given, selected again, this HT. So this is the best reclassifier in this loop, in this current iteration. Let's say it is first iteration, T number 1. Okay, it is the best classifier. By the way, for every sample, because it is not 100% perfect, right? So it can succeed to classify certain samples, but sometimes it can fail. Yes, exactly. Okay, so, oops, oh, no. Okay, so let me write down HT equals 1 and Y equals 1. Then 1 minus 1 equals 0. Okay, HT equals 0 and Y equals 0. Then 0 minus 0 equals 0. Okay. By the way, so these two cases, HT say 1, Y say 1. HT say 0, Y say 0. It is correct case. Okay. So W and X, especially X include, positive and negative samples, all the samples, right? So some X has label 1, some X has label 0. By the way, we classify HT, say the correct answer, oh, you are 1, oh, you are 0. Or if the answer is correct, then this part, absolute HT minus Y, becomes, 0. 1, 1, 0, 0, 1, 0. It is successful case. Then, okay, so let's discuss about just this case. When this reclassify HT is has succeeded to classify current Xi, whether it is 0 or 1. Okay, then what happens to this beta? Then beta's exponent is becoming 1 minus 0. 1 minus 0. It is 1. The beta exponent 1, power 1, equals beta. Is that correct? So, okay. So, when the classification is successful for certain sample xi, then beta is multiplied to the weight of that xi. The corresponding weight is updated by multiplied by beta. Clear? Okay. So let's think about the other case. When fail, okay. So this HT failed to classify certain xi, another one. Okay, I'm now checking other testing, other sample xi. Okay, it can be x200 now. HT 200 and its yi equal is different. So 1, 0 or 0, 1. Then this part, this absolute part, is becoming, in the case, HT minus Y. In unsuccessful case equals becoming 1. 1, 0, 1 minus 0 or 0 minus 1 is becoming 1. Okay. Then what happens to the exponent part of beta? It is becoming 1 minus 1 equals 0. Okay, so beta power 0 equals 1. So instead of beta, in that case, when this classifier fails to classify this image, sample. Okay, then instead of beta, just 1 is multiplied to W. Yes, exactly. Okay, something power to 0 equals just 1. So beta is, the beta term is disappearing in this formula. Okay, that's the role of this exponent. Okay, 1 minus absolute of h minus 1. Okay, it means W is not changing. Okay, so now you have to remember, we now have just one selected reclassifier, HT. Okay, when I apply this HT to every sample image. Okay, by the way, when let's say, I am the classifier HT. When I can classify the given image correctly, then I am updating the weight. I'm changing the weight by multiplying beta, whether it is less than 1 or larger than 1. Okay? By the way, for certain sample, I cannot classify this image correctly. Then I don't change it because I cannot say, I cannot classify that, right? I have no right to change the weight of that image. If I can classify the image, the sample, correctly, then I update the sample, the weight of the sample. Okay? So it is, it looks a little bit complicated. Okay? So we have many different important points here. Okay? Is that clear? Yes. Okay. So we are updating the weight, of samples just when I can classify the sample well, correctly. Okay. Yeah. So when, let's say in the worst case, when beta equals 0, when there is, we have completely, perfect reclassifier, 100% reclassifier. I'm talking, I'm just assuming the, the extreme case. Okay. So 100% correct. Then beta equals 0. Okay. And all the weight, when I say 100%, it means I can classify everything correctly. Okay. Because it's 100%. Then beta equals 0, and we can update all the samples because I can classify all of them. Then W equals is becoming all 0. Okay, yeah, W is becoming all 0 because 0 is multiplied to every W. So the new W here, WT plus 1, comma I. So here again the T means the iteration number index, time index, right? So here when we say WT plus 1, what does that mean? So WT plus 1 is calculated based on WT T, comma I, right? From WT for the same sample I. Okay, it means the WT plus 1I means it is the weight for the next iteration. Okay, the next is, if I am now T equals 1, then the next, the new W is T W2. Okay, so here the W2 means, it will be used for the next second loop to calculate the error. Okay, so in this sense, we are using WT plus 1. So WT plus 1 is the updated weight. WT HT, I is current weight. Okay, so from the chosen the winner reclassifier HT's point of view, I update the weight of samples just when I classify them. If I cannot classify, it means I have no right to change. Okay, because I cannot classify that, so I don't know about it. But for the samples I can classify, then I can clearly say, and I have the right to update their weight. I can clearly say, if it should go up or down. It should be increased or decreased according to the data, my error. Okay. So by the way, in this way, okay, some weights are not changing. Okay, but some weights are changed. Okay, but how they change? It is depending on the beta value, E over 1 minus E. Okay, so for some weights not changing, but changing weights according to beta, they can decrease or they can increase. Okay, is it clear? Okay, so let's go to the next slide. So this is, let's go to slide, 32. Let me move to 32, page 32. Okay, so this is explaining this step a little bit clearly. Okay, from original formula, WT plus 1 I equals WTI beta power of 1 minus absolute H minus Y. Okay, so it means for well-classified image by HT, we are updating W with beta. Okay, misclassified images, we are not updating, but there is no change. By the way, when we are updating the weight, it can be decreased and it can be increased. So when error is less than 0.5, then weight will be decreased. Okay. When the other case, when error is larger than 0.5, then the weight of the left case, not everything, okay, not every weight, but just some weights, they can be decreased, they can increase. Okay, is that clear? Okay, so let's see some example. Okay, so just to simplify the problem, I just considered just 10 weights. So actually we have thousands of tens of thousands of weights. Okay, but because we have so many samples, so let's assume we have just 10 samples, just to simplify the problem. Then the weight, initial weights normalized because they all have the same weights, right? So every weight will be 0.1, 0.1, 0.1. Okay. Then after one iteration, so when we have selected one HT, H1, the best reclassifier, then based on the weight update formula, then we update the weight of well-classified samples. So in this way, let's say the beta is less than 1. It means error is less than 0.5. Okay, then the well-classified samples are, so their weights are decreasing in this way. Okay, and these classified samples just stay in the number of 0.1. Some of them just here as 0.1 constant, and some of them will be decreased. Like 0.8 or 0.7, blah blah blah. Okay. Then what happens? So finally, the result is HT is becoming less probable to be a winner, to be selected. Here the winner means the selected one, right? So to be a winner again. Okay. How is it happening? Let me show you. If I sort these weights like this. Okay. So from initial weights, when error was I'm sorry, beta, not error. Okay. Beta is 0.6. It means error was less than 0.5. Okay, just for example, this is very simplified example. Then I sorted the value, I moved the position. The well classified samples as this is becoming smaller than 0.1. The initial value was 0.1 for every weight. Okay, and misclassified samples will have large 0.1 errors. So they have large weight. So okay. Okay. So in this case, I can understand your question. Okay, let's discuss about this slide first. Okay, 35 in slide 35. Okay. So finally, in this case, when we are in the next iteration, the second, let's discuss the situation of second iteration. In the second iteration, now the initial weights are like this. By the way, they should be normalized first. Okay, so they may not have exactly the same value like 0.1 and some less than 0.1. Okay, they can be a little bit bigger, right? Because the sum of the weights should be 1. They normalized measure. Okay. Anyway, so this is just kind of simulation. So just ignore the the normalization. Okay. Then for feature 1, so here feature 1 was the previous feature that was selected as the best one. The feature of reclassifier 1, the first reclassifier selected. Okay. Then we have this reject. Then if we run the same error calculation again, then what happens? For well classified samples, the error is less than 0.4, right? Because we have 4 well classified samples. But error, by the way, error is calculated based on the misclassified samples. When the classification, remember the error formula? Is that correct? So we are calculating the error when we misclassify any sample. When we classify well correctly, then we are not accumulating the weight, right? So error is accumulating the weight of misclassified sample. So for feature one, we are just accumulating this, blue region, misclassified samples weight. Then the error is becoming 0.6. Is that clear? By the way, let's consider any other feature 2 now. feature 2. By the way, in this feature is very working in a exactly, just assuming, just assuming exactly opposite way of feature 1. So feature 2 misclassify the first 4 samples and will classify the other 6 samples. Okay, then the error of feature 2 is calculated as 0.2. Let's say the every error of the left 4 early 4 samples 0.05. Okay, then it is becoming 0.2. So just considering these two features, these two weak classifiers, which one should be selected in this second iteration? Which one should be selected? Yeah, so second one, okay, feature 2 should be selected, okay, because error is less, the E2 error is less than E1, okay, yeah, so what is happening in this case, right? So when feature 1 was selected as a best reclassifier in the first iteration, then because the feature is not changing, the weight is changing in every iteration, what is changing is the weight. All others are the same. So the samples are the same, and the features are the same, threshold, everything is the same. Okay, just based on the changed weight. Now in the second iteration, instead of a feature 1, even though feature 1 is the same, okay, now the feature 2 is selected, okay, in the second iteration. Yes, exactly. So in this way, every iteration, normally in the paper, we set the maximum iteration number 2000. It means, okay, I need 2000 features to construct the final classifier. Okay, if you need just like 1000, then you can set the maximum iteration number 1000. Okay, whatever number. Okay, so we need 2000 iterations, features, reclassifiers. Then we are iterating 2000 times, and every 2000 iteration, we are selecting. We try to select different reclassifiers in this way. So feature 1 is once selected, okay, then we try to select feature 2 instead of feature 1 again. So if in this case, if we don't update the weight in this way, then what happens? In the second iteration, which feature will be selected? Yeah, feature 1 will be selected again. Okay? Yeah. Yes. So there is no change, right? Every iteration, just one feature, feature 1, feature 1, feature 1, feature 1, no change. So then there is no meaning, to do this kind of training. Okay? The main purpose of this training is to select a set of good features. Okay, so it should not be just 1. Okay, so in this sense, by updating the weight, so this is kind of mechanism, in the next iteration, we have another chance to find, different, weak class, different feature, different, best feature, different, best weak classifier. Yes. Is it clear now? So that is the weight update process. Okay. Any question? Okay, good. Thank you. And I think we can have a break now. Okay, let's have 10-minute break. Okay, so see you in 10 minutes. Okay, so in this way, in every iteration, we can update, we can calculate error and select the best or weak classifier. Hopefully, it can be different every frame, but some possibly, there is a chance, same feature can be selected again in the worst case. But generally, every frame, every iteration, different, reclassifier will be selected in this way. Okay? And once the new reclassifier is selected, then we update the weight, and in the next iteration, we select another reclassifier and update weight. So selecting best classifier and update weight. Select, update. Select, update. So this is actually the main, thing, it is doing in every, loop. Okay. So after this iteration, let me show you. Okay. After this iteration, all the iteration, I think I'd better show you this slide. Back. Oops. Yeah. Okay. Let's go back to slide 30. 30. Okay. Okay. So in this step 3, okay, this is the whole. All the step 3 is for loop. Okay. From iteration number 1 to large T. Here, the large T is normally 2000 in the paper. Okay. So again, you can change it later. Okay. So every 2000 iteration, we are repeating this A-step normalizing weight, error calculation, choose the best classifier, and update weight. Okay. So as a result of this iteration, what can we generate? So weight is just, temporary value just used inside this for loop. Okay. So we are not saving the weight after every iteration. So what we are saving from this iteration is, first of all, the HT, or which reclassifier is selected. Its original, maybe index number. Okay. Of this time, we copy the selected reclassifier into every HT. So H1, H2, H3, H4 in this way. Okay. And we also can save error. Oh, the error of H100 was like this. Okay. Okay. So for example, original index H100 was selected as HT. Okay, then each error E100 value can be saved together with this HT. Okay, and it's beta. So when we know error, then we can calculate beta. Okay, so all these, weak classifier and its error and its beta are all recorded per every T. All the weak classifiers from H1 to H2000, okay, that is the result weak classifier. Again, in this case, every selected weak classifier includes is saving error and beta together for the later usage. Okay. Indication, is it clear? So now finally, after 2000 iteration, for example, now we can have 2000 weak classifiers and their errors should be same. Okay. So based on these 2000, selected weak classifiers, finally, as a result of AWS training, finally, we can have one strong classifier. So this is the formula of strong classifier. Okay. So the symbol of strong classifier is now HX. It doesn't have index. Okay, just HX means the final strong classifier. Okay, so this strong classifier is also binary classification, 1 or 0. Oh, in this sense, it looks like a little bit similar to weak classifier, right? So actually, basically, strong classifier is combination of weak classifier. Okay, so this HX can give us the result 1 positive when the left part here, okay, sum of alpha weighted, weak classifier results, HT, is less than or sum of alpha. I'm sorry, larger than or equal to or sum of alpha. Then this strong classifier HX will have result 1. Okay, so it looks, it is a new formula, right? So it looks a little bit complicated. Yes, X is pure sample. Yes, exactly. So X is sample. H is, HT. You remember what is HT, right? So this T is the same T from our previous, iteration. Okay, so we have 2000 HT. So this sum, sigma, the left one, from T equals 1 to large T. So this means 2000 weak classifiers. So this is actually sum of the results of 2000 weak classifiers. So HTX itself, the weak classifier, the selected weak classifier, HTX, and its results can be 0 or 1. Sometimes it can be 1, sometimes it can be 0. Okay. By the way, okay, so as as you asked, right? Someone asked what is alpha. So yeah, this is what we have to understand. Okay, once more. Okay, so what is alpha? HT, we know what is HT again. Okay, HT can be sometimes 1, sometimes 0. Okay, so very simply saying, when many HT say, oh, it is 1, then the final strong classifier should answer 1. Okay? So when many HT say, oh, it is 0, it is non-phase, then final decision will be non-phase. Is that correct? Okay, so how many of you watched the U.S. president election last night? Did you watch the election? Okay, so I also I didn't watch the whole thing, but I sometimes check the results because everybody in the world is interested in the election. The result was, do you like the results? Okay, so a lot of people, as yeah, it was very unexpected, and a lot of people, disappointed, right? Okay. Anyway, some people, are happy, very happy. Anyway, anyways, okay, yeah, I just like, yeah, yeah. Okay. By the way, this formula is very similar to election. Okay. So in this case, HT, the reclassifier, can be regarded as the voters. Okay. The citizens. Okay. So we have 2,000 voters. And so I'm showing one picture, face picture X, like this, face picture. And I'm asking to this, 2,000 people, okay? And I'm asking, if it is face or not. Okay, if many of them say not 100%, but if many of them say, oh, Hillary should be president, okay? Let's say Hillary is 1, Trump is 0, okay? Many people say, okay, out of 2,000, for example, 1,900 people say 1, Hillary. Then Hillary will be president, right? By the way, like the last night, okay, more than almost 1,020 out of 2,000 say Trump, 0. Then the final result will be 0. So in case of election, how do we determine? We just sum the votes. Okay, how many 1, how many 0 between Hillary and Trump. Okay, so many more sum value will win the election, will be the president. Is that correct? Yeah. So in that sense, this formula is very similar to that kind of election, the democracy. Okay. So every reclassifier is kind of voters. Okay. Some people say 1, some people say 0, but some of them, the sigma of all the opinion of reclassifiers, every people, okay, every voters. So we can, because we cannot be like everybody unanimous, right? Everybody can have same opinion. It is not possible. Okay, some people like Hillary, some people like the Trump, right? So we cannot be just one answer. So, by the way, if many reclassifiers say, oh, this is space, then we can say it's space. So by summing, okay, this H result, HT, we want to determine if it is space or not. Okay, if half of the people, half of the reclassifier, more than half, say space, number one, phase, then the result will be phase. So that's the meaning of this, 1/2 half. So we have alpha here, right? Alpha is a little bit strange. So let's talk about alpha a little bit later. Okay. So more than half is saying it is 1, then it is becoming 1. Else, it means less than, half, right? Else, then it is non-phase. That is the kind of very simple and straightforward, election-based decision making. Okay, so again, we are asking opinion of every reclassifier because every individual is very weak. Yes, exactly. Okay, every individual is weak. They sometimes they can misunderstand. Sometimes, so well-educated people, they are talking about that kind of issues a lot, right? So, or, immigrants, they have some, prejudice, and, poorly educated people and white people, okay, they can have some other opinion, other prejudice. So every single person can have, different point of view and different opinion. Okay, so every single reclassifier cannot be perfect. By the way, some of all the opinion we believe in democracy at least, okay, we believe the sum of all the opinion can give us a better solution. That is our current general election system, even though sometimes it fails. Okay. Anyways, so this formula is the same, right? Have larger than her, yeah, something like that. Okay. If the sum of h is larger than half, then it is phase. That is our strong classifier. Yes, we didn't discuss about alpha yet. Okay. Okay. So from now, by the way, okay. So it is straightforward, right? It is election system, right? In some of we want to accumulate all the results of weak classifiers to make a better, stronger decision. Okay. By the way, here there is one mysterious symbol alpha. So what is alpha? So this is the formula of alpha. Alpha equals alpha t. So alpha is also corresponding to every weak classifier. So we are using the index number t. Okay. So you are not using the index number j anymore, right? Okay. So j is used the index number of every weak classifier inside the AWS algorithm. Okay. Now we have finished the AWS. Okay. Then now we have T 2000, just 2000, not 180,000. Okay. So alpha T is calculated in this way: log function of 1 over beta T. Oh, what is this? Then what happens? Okay, beta was actually E over 1 minus E. Okay, alpha is log of 1 over beta. So let's go to the next page. Okay, let's go to the next page first. Okay, I want to show you this graph to understand the meaning of alpha. Okay, so I try to draw, this graph, okay, for your better understanding. Okay, so can you see this page 39? So this x-axis is again error. Okay, everything is about error, right? The beta is calculated on error E, and alpha is calculated based on beta. So actually, alpha is related to error E. Finally, right? So this x-axis is error E. Then what was the What was the beta graph? You remember beta graph? I didn't draw a beta graph here. So beta was like this. Remember? Can you see the green line? Yes, yeah. So this is beta graph, right? Then 1 over beta is this blue line. Is it clear? This blue line. 1 over beta is a kind of, inverse of, green graph. Is that clear? Okay. Then alpha is log function of 1 over beta. Then, so it is not, easy to, calculate it straightforwardly, right? So when I use the calculator, this red graph is alpha. Okay. Anyway, in this way, we can now see the relationship. So when we say just like alpha based on beta, it looks a little bit strange. But finally, the relationship between alpha and error, okay, is like this. So finally, when we have error value between just 0 and 1, okay, when E is increasing, alpha is decreasing between 0 and 1, right? When E is decreasing to 0, then alpha is becoming infinite number. Is that clear? When E is approaching to 1, what happens? Alpha is becoming negative infinite. Is it clear? So one clear thing here is, alpha is inversely proportional to error. So for example, let's compare H1 and H2. Okay, when H1, the error is less than 0.5, so very small error. It is a good classifier, right? H2, this error is almost like 0.9. It's alpha. It is a bad classifier relatively. So which one is better? H1 because it's better because it has much less error. Okay, right? Then this alpha, H1's alpha is positive like 0.4. H2 reclassifier's alpha is becoming negative, almost like -1 here. Okay, so when we have a good reclassifier relatively, okay, so now we have selected 2000 reclassifiers, right? The best reclassifiers, good reclassifiers. But among them, relatively, when we compare their error, okay, relatively, good classifiers can have bigger alpha, larger than 0. It means good classifier. It means, its error is less than 0.5. Okay? So, when good classifier has larger number, positive big number, bad classifier can have, negative big number. There's small number, negative, right? So small number. So big classifier will have bigger alpha. Is that clear? So alpha is inversely here. Alpha is inversely proportional to error. So finally, exactly, yeah, someone is correct. Okay, so finally, good alpha is representing, how good is every, every weak classifier. In other words, it is different kind of weights of every weak classifier. In other words, a better representation is, it is a kind of confidence value. So it's just, to understand easily, confidence value of every weak classifier. So if we have very big alpha for a certain, weak classifier, then we can believe the results of that weak classifier, because that weak classifier will give us much less error. If we have small or negative alpha, it means we cannot believe that weak classifier. Is that right? Yes, big error. It will give me big error, so we cannot believe it. Okay, so alpha is controlling, the confidence of every weak classifier. Is that correct? Okay. So in that sense, so this election system again is a little bit different from our current, election system. Okay. So when we are asking, opinion to everybody, okay. Sometimes, so let's guess your everyday, kind of situation. So sometimes, when you want to determine something, where do I have to go for lunch? Which restaurant? If you are living in downtown and there are many restaurants around, lunchtime you want to go to a good restaurant. So you can ask your friends, which restaurant is good? Okay, so you can gather some information. You can get some votes. Somebody say A is good, somebody say B is better, blah, blah, blah. Okay, so who do you want to believe? So if you, even though you have many friends, right? Some of your friends can have very high, reliability and, uh, high confidence, right? You can believe them. Then you can give more weight on their opinion. There's some guys, even though they are you're working together with them, but you cannot believe them. Okay? Then even though they say something, you don't believe them, right? You are giving very small or even negative confidence, negative belief for their opinion. Okay? So this alpha is the kind of, belief or confidence value. Okay? So good reclassifier will give us good big alpha, okay, big value accumulated, and bad reclassifier can give us, smaller or even negative, results. Okay, so this, alpha weighted sum now finally give us better results, because uh, uh, better results than, without alpha, right? Because every weak classifier can have, different error. Okay, so they can have different confidence, different belief. Okay, so the sum of alpha means all the sum of alpha. So we have this kind of, for example, 8 alpha numbers. Some of the weak classifier has, alpha 0.4, 5, 0.6, 0.9. Okay, and some of them may have some value. Okay, so half of the sum can be calculated as a threshold. So the sum of the weighted alpha weighted weak classifier results is larger than the threshold. Then we can say, oh, it is base. It is 1 positive. Okay, that is the concept of weak classifier and strong classifier. Okay, so is it clear now? Yes, yeah. So even though we cannot draw the graph by ourselves, okay, we need the calculators, but you just need to remember alpha is inverse proportional to error, so it can give us the confidence value of every weak classifier. So when we are summing the opinion of every weak classifier, we are considering the confidence of every weak classifier instead of treating them all the same. Okay, so almost done. And any question about alpha and strong classifier? The strong classifier is now finished. Your question, alpha determines threshold graph. Okay, so what do you mean threshold graph? Alpha determines, you can say alpha determines how much you can believe the weak classifier. The confidence is, in other words, confidence or belief. Okay, how much I can believe the weak classifier. If we have big alpha, then we can rely on that weak classifier. If we have very small alpha, like negative, then we cannot believe that weak classifier. So in this way, we are now, they're not equals, right? Weak classifiers are not equal because they have different error previously. Some of your friends lied a lot to you, then you cannot believe their opinion. By the way, there is somebody you can believe, then you can rely on their opinion a lot, right? Like your parents and your husband or wife, right? Okay, any other question? All clear? Good. Okay, thank you. So finally, after data boost learning, we can generate these results. So for 2000, in this case, large T was 2000. For 2000 iteration, every iteration we generate H1. Again, this one is not J, okay? This is small t index. H1 and H1 is corresponding to, F1, okay? And it's delta threshold and P as well, okay, anyway. And finally, we have alpha value of H1. For example, it can be 0.4, okay? And second iteration H2 also generates alpha 2. So in this case, -1. H3, alpha 0.9. So we are storing all this information of every selected weak classifier into the kind of database or file, okay? And then we can use it for a strong classifier at the time of classification. So again, this is talking about learning process. Okay, learning process of AdaBoost is generating all these features, weak classifiers, and alpha. Their alpha values, right? So this is the result of AdaBoost learning. Then traditional AdaBoost classifiers just construct one strong classifier based on these 2000 weak classifiers and try to make the final decision per every image, per every sample. Okay? Oh, this is phase, this is not phase. Okay? The best, not the best, reclassifier is 0.9. But even though, so H3 has the alpha 0.9, right? But even though H3 has the maximum alpha, but again, even though it has very high confidence alpha value, but we cannot make a decision just using H3. H1 has 0.4. Okay, so it is not like 0.9, smaller value, but we still need to use its opinion. So in this way, we are adding all the opinions, okay, of all the 2000 reclassifiers. Okay, so even though, again, even though one reclassifier has very high, alpha, it can affect my decision a lot, but I'm not making decisions just based on that opinion, because just one reclassifier is not perfect. One person is not perfect to select our president. Okay, so we need to gather lots of opinions, even though sometimes it's not working. Okay, so your question is we need to rank results. What do you mean rank? Sorting? You mean sorting? Yeah, we can store. Okay, so we can store in terms of yes. Finally, in the next step, we are going to use the sorting. Okay, but this step, just we still need to store. Okay, but as you said, we need to sort them finally. But okay, so let me show you this formula again. The strong classifier. When we are adding the result in this way, sigma formula, is the rank any meaning or not? It doesn't mean anything, right? Whether it is sorted or not sorted, the result is the same. Is that clear? Yeah. So it doesn't matter, just in terms of this strong classifier. By the way, next step, we have just one more step left. It is cascaded classifier. Okay. For that process, we have to sort these, reclassifiers based on the alpha values. So we'll talk about it later. Okay. But just for this kind of strong classifier, this kind of standard strong classifier, we don't need to sort that. And Dental Lab asked the question, what will we do in order to make a decision in this case? So this formula is the final decision. Okay, so whenever we have a new picture, X, okay, then we calculate for 2000, reclassifiers, calculate all the results of reclassifiers 0, 0 or 1 and multiply their alpha, and we are calculating the sum of all these alpha values, alpha weighted H values, and then we are checking the value with the threshold, the right hand side, the half of or the sum of alpha. Okay, then we can say it is phase. We can make the decision, oh, this is phase or non-phase. Okay. Any other question? All clear? Okay. So today I want to I believe you might have understood the basic algorithm, but for better understanding, okay. Now the question: we sum alpha 1, alpha 2, alpha 3 and compare it with the threshold. Yes, yes. By the way, not all the alpha, okay? When the H say 0, then that alpha is not added. Okay, so let's consider, the election system. Okay, so just let me explain a little bit more, because some people, some students can be maybe confused. Okay, so let's consider this election system. Okay, so is there any American here? There's not. Okay, so let me just an example. Okay, this is not real. Okay, so in United States, some people voted for Hillary, some people voted for Trump. It just counts the number. So they have the representatives, right, whatever. Okay, counted the number of supporting Hillary, counted number of voters, supporting Trump. Okay, so we can just uh, make the decision, right? Who is which one is? Let's say Hillary is number one, and label 1, and Trump is 0. So how many number 1 do we have? It is larger than half, then we can say Hillary is president. Okay. If it is less than half, we can say Trump is president. By the way, if we give alpha to this system, okay, if the voter, every voter has different confidence value. Okay, so for example, if we give well-educated, more intelligent people more alpha, and the other guys less alpha, then the sum of the alpha value who voted Clinton, okay, Hillary, can have some bigger value than Trump, even though the number of the votes are less than Trump. Make sense? Okay. Anyway, so yeah. Okay. Any other question? Okay. So today, for your better understanding, I want to give you one task, another task. By the way, have you finished the first assignment, first test? To summarize the paper? Okay, not? Okay. Yeah, so this is the second one. Okay. I haven't posted, this test to the e-learning system, so I'll do that right after this class. Okay. So this is AWS feature selection test. Okay, no problem, no problem. Okay. So this is the kind of experiment to understand, integral image, and to understand highlight feature, and to understand feature selection, as we have studied. Okay, this is not kind of full, face detection or full AWS algorithm. This is kind of just a partial, very small, simplified, experiment. Okay, so I will provide you, these two different zip files. So I will upload them to the to the folder. Okay, so face.zip will include positive sample data, pictures. Okay, non-face.zip will include negative sample images. It's not so many. It's not the real case, experiment, right? So it's not so many. Okay. Okay. And this is the description of the task. First of all, you have to load the positive and negative sample images. They are 19 by 19. Okay. And you have to generate integral images for all sample images. Do you know how to calculate integral image? So this is very small images, right? So I intentionally made it very small. Normally the image size can be bigger, right? Okay, 19 by 19. And you have to calculate the integral images. Okay, and then you have to calculate the feature values for all sample images using the integral image. So as for the feature value, I will give you two features. We don't have, we don't need to do 180,000. Okay, you don't need to do that. So I will give you in the next page. I'll give you feature 1 and feature 2. Okay, so calculate two feature values for every sample image using, you have to use integral image. Okay, and based on the feature value, calculate the threshold of every feature and P as well. So you have to construct the reclassifier. Okay, and then you can calculate error of these two features. Okay, and based on the error, select one of the features, one of the two features as the best feature, better feature. Okay, and next page, okay, this is feature 1. Inside this 19 by 19 images, okay, for every sample, okay. Then feature 1 is two rectangle vertical feature. So this white rectangle, the left top corner position is 5,5. Right bottom is 10,8. Okay. The black rectangle, the left top corner is 5,9 and right bottom corner is 10,12. Okay. And feature 2 is also two rectangle feature, but its position is different. Okay, so right rectangle has this position 10, 10, 15, 13. Black rectangle 10, 14, 15, 17. Okay, so you know how to calculate this feature, right? White rectangle minus black rectangle sum using integral image. So you should generate the integral image first, and then you can calculate these two features, feature 1, feature 2. Okay, then based on these two features, okay, you have to calculate thresholds by analyzing the every feature value. Okay, threshold of feature 1, threshold of feature 2, and then you can calculate the error using the given phase and non-phase images. And finally, select the smaller error feature. Is that clear? Then the results. So you have to submit source code, and you have to submit integral image because you have to generate integral images. Okay, and provide one report as a PDF file. Okay, so in this report, you have to list all feature values, all sample images. You don't have many samples, right? So you can list the sample feature values or sample images first, and reclassifier with threshold. Okay, every feature. So you should have two request files. Request file 1, blah, 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 request file 2. You want to use MATLAB? Yes, you can use MATLAB. You can use, general, I don't want to, limit the language because different students may be familiar to different language, right? So you can use both general languages. Don't use, actually, in my case, C++ is preferred, actually. But C++, C#, Java, MATLAB are good, okay? But don't use any very unfamiliar or too new language, okay? Script language is not allowed, okay? Just general language. JavaScript is not good, okay? So general programming language. Anybody has any special language to use? C++, Java, C#, MATLAB is good, okay? Because many computer vision, MATLAB is good. PHP, no. You have to use PHP. PHP, yeah, I just need the source code and the widgets. So NetBeans is okay. Doesn't matter. So I think Python is still good because these days we have many library imported to Python, so you can use Python. But I haven't heard PHP is good for image processing and computer vision. C# is good. Good. Okay. Yeah. Okay. So you can use just to if you want to use like a library such as OpenCV, you can use that kind of library just to read the image, or just to read the image. Okay, so you have to use some library to read the image, right? So if you are using MATLAB, you may use some MATLAB function to read the image, right? So it is just read and understand and parse the image. You can use some library. But for this calculation, to calculate integral image, to calculate features, to calculate threshold, error, okay, it should be done by your own code. It's a kind of practice, okay? And so you have to list errors, and you have to give the alpha as well, alpha, okay? So this PDF file actually include all the results, okay? Submit the PDF together with the source code and integral images. Is it clear? Okay, so after this class, I will upload I post the assignment in the e-learning system, and I will upload the base.zip and non-base.zip and give you the link in the post, in the assignment post. Okay, so just refer to the assignment posting. Okay, so I think I can give you some weeks. So how many weeks do you want? How many weeks do you think based on your schedule, I mean your number of classes, courses, how many weeks do you need for this assignment? Give me some idea. Two weeks. Okay, everybody agree? 2 weeks? From my experience, previous experience, for some students, 2 weeks a little bit short, right? Oh, really? Just 2 weeks? 3 weeks? 2 days? Oh my God. Okay, let's say 3 weeks. Okay, 3 weeks. Is 3 weeks okay now? Okay, I think 2 weeks not so, yeah, not enough. Okay, 3 weeks. But in the worst case, okay, if you cannot submit in 3 weeks, then you still can submit later. Okay, late submission is still acceptable. But maybe if it's too much late, then there will be some kind of I will give some penalty, but still good. Okay. Yes, sure, sure. Yeah. So when I determine the weeks, then I will post. I will assign the date in the e-learning system. Okay. So I post it right away after this class after today. Okay. Okay. Thank you very much. That was for today, and I think it was very on time, exactly on time. And next week we don't have class tomorrow, right? And it is also the same holiday in Canada as well. Okay. Okay. Have a nice holiday, long weekend. And next week we move to the final topic of this algorithm, face detection, that is cascaded classifier. So yeah, let's discuss about that algorithm next week. Okay, thank you very much. Whenever you have any question about assignments or anything else, just contact me via email or Facebook group. Okay, thank you. Have a nice weekend. Thank you very much. Bye.